So in this video, we're going to set up the table we're going to use to work through a titration problem and go through the first few steps in that process. Specifically, we're going to look at a strong acid and a strong base in this example. So I'm working with 100 milliliters of 0.15 molar HCl and 0.3 molar sodium hydroxide. And the question is, what is the pH after additions of 0, 1, 10, 48, 50, 52, and 75 milliliters of the base have been added? So in a sense, this is not one problem. It's actually 7 problems. And so what we're going to do is we're going to try to find a way to organize ourselves and keep track of what's going on. So we're going to make a table. And in this table we're going to have a bunch of columns. The first column we're going to have is for the milliliters of base that have been added. Second column we're going to have is going to be for the total volume. The next column, I'm just going to write ma-va, but what it really is we're calculating the moles of the acid. Column after that is going to be mib-vib, molarity of the base times the volume of the base, but that's going to work out to be the moles of the base, and we're going to use the rest of the space over here for calculations. So very quickly I can sort of start this off. I know the milliliters of base added, first it was 0, then 1, then 10, 48, 50, 52, and 75 bottom. So I've got this all set up. Now the total volume, I started with 100 milliliters of the acid, and so before I've added any base, the total volume will be 100 milliliters. Now I'm going to leave sig figs out of my table just so I can write a little larger and make it more clear, but of course they still matter. After I've added 1 milliliter of base, the total will be 101 milliliters. Now, here's where it becomes an issue. This 10 could mean one of two things. It could mean 10 milliliters beyond this point, or it could mean a total of 10. And generally speaking, we mean a total of 10. If we meant 10 added on top of this, it would say something like an additional 10 milliliters. Because it doesn't say that, we're assuming this is a total volume, which means when I put them together, it'll be 110 milliliters. So 100 milliliters of the acid plus 10 that I've added. Likewise, this will be 148, 150, 152, 175. MAVA, to determine the moles of the acid, molarity of the acid times volume of the acid. So this is going to be 0.150 molar. Now, because molarity is moles per liter, I need to put my volume of the acid in liters. So this is going to be 0.100 liters. I do that math, it ends up being 0.0150, and that's moles. Now, I'm writing moles here. I'm going to be lazy and not write moles for the rest of the table, again, to give myself some more space. Now, in this row, when we try to figure out the molarity of the acid and the volume of the acid, what matters is that I haven't added any additional acid at all. I've added some base, but the amount of acid that I started with hasn't changed at all. So this number that I've calculated here is actually going to be the same the entire way down through the table because I'm not adding any more acid. So I'm just going to copy that down, 0.0150, 0.0150, and straight down through the table. Now, this value is going to change because I'm adding base through the entire problem. So each step I'm going to be adding some base. So initially, when I haven't added any base, I don't really need to do any math. There's no base. For the next step, I'm going to take the molarity of the base, 0.300 molar, times the volume. Again, volume here has to be in liters. So it's going to be 0.001 liters. It's going to give me 0.0003 moles of the base. Following the same logic, this is going to be 0.3 times 0.01 liters, gives me 0.0030 moles. Same logic, 0.3 times 0.048, which is going to give me 0.0144. 0.3 times 0.05 is going to give me 0.0150. 0.3 times 0.052 is going to give me 0.0156, and 0.3 times 0.075 is going to give me 0.0225. And so that gives me all those values. This lets me set it up. Now, what I'm going to do is I'm going to do the same subtraction problem I was doing when we talked about the stoichiometry of titration. I'm going to do a little subtraction and see what's left. Here there's no subtraction to do, but here there is. Again, I'm adding a strong base. Strong bases react completely, so I'm going to use up all of that base, leaving me none. Because it's a 1-to-1 ratio, HCl and NaOH react 1-to-1, I'm going to use up the same amount of acid. So this is going to be minus 0.0003, leaving me 0.0147 moles of the acid after that reaction. Again, the same process here. Strong base reacts completely. I'm going to use up all of that. I'm going to use up the same amount of this, leaving me 0.0120 moles. Same process again. I'm going to use up all of this. I'm going to use up 0.0144 of this, leaving me 0.0006 moles of the acid left. Now this step is interesting because I now have exactly as many moles of the base as I started with acid. This point is called the equivalence point because the two amounts are equivalent. So when I use up all of this, I'm also going to use up all of that. Beyond that point, what I've now done is I've added more base than I had acid. It's still going to go to completion. It's still 1-to-1, but now I'm going to be running out of the acid. The acid is now the limiting reagent. So this is going to go to 0. I'm going to use up 0.0150 of this, leaving me 0.0006 moles, in this case of the base. Same thing happens here. My acid is the limiting reagent because it's smaller, so I'm going to use up all of it. Subtract 0.0150. It's going to leave me 0.0075 moles there.